Okay, so let's carry on with muscle contraction. Now, here's a page that shows you a list of the important molecules that we'll be talking about when we're talking about muscle contraction. Okay, so we've talked about acetylcholine already. So that's the neurotransmitter that's going to carry information from the nervous system to the motor end organ, which is going to cause the muscle to contract. The next one we have is the calcium ion. The calcium ion is released from the sarcoplasmic reticulum. And what calcium does is it shifts the troponin and the tropomyosin off the actin filament, and that'll expose the actin binding sites. We have two more molecules down towards the bottom, troponin and tropomyosin. Now these are going to be molecules that block the active sites, the sites where actin filaments can form cross bridges. Okay, so tropomyosin and troponin have the same function, so they'll block the binding sites on the actin fiber where cross bridges can form with the myosin protein. Now, I skipped over ADP and ATP because those are two molecules of energy molecules. ATP is the most popular energy molecule we'll have in our body. Okay, when we do basic metabolism, we take complex molecules and we break them down in order to get as many molecules of ATP as we can. If you think about how these are related, ADP is adenosine diphosphate, which means 2. Adenosine triphosphate is tri, which means 3. So the molecule kind of looks like this. We've got a box here, and it goes to P, 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 and that's ATP. And for ADP, we've got our little box, and then it goes to 2 molecules of phosphate. Now, the real high energy bond is right here. Okay, when we break this bond right here, we get lots and lots of energy. And when we break that bond, if we look at what's gone when we break that bond, we've converted ATP back into ADP. So that's the relationship between ATP and ADP. There are two molecules of two energy molecules. ATP has the higher energy, and that's the one that we kind of want, and ADP is left over when we use up ATP. Now, in this context, ATP is going to function to detach the myosin heads and move them back to a ready state. So after the cross bridge has been made, ATP will use to break that bond so that the myosin can return to normal and then form another cross bridge to increase contraction. Okay, so those are the important molecules when we're talking about muscle contraction. Now, the next couple of slides are important because they're going to go through step by step of what happens during muscle contraction. Okay, so let's start with number 1, and we're going to start where acetylcholine is released from the neuron ending into the synaptic cliff, so into the gap in the synapse between the nervous system and the musculature. Okay, now once the acetylcholine binds or passes through the synapse, it'll bind to the motor end plate on the muscle fiber, and that will cause an action potential. Okay, the action potential is going to travel to the sarcoplasmic reticulum. The sarcoplasmic reticulum is going to release calcium into the cytoplasm. And when the calcium is released and it comes in contact with the actin filament, it's going to shift the troponin and the tropomyosin off those thin active filaments, and it's going to expose the binding sites where myosin can form cross bridges with the actin. Now, once those molecules have moved out of the way, those myosin heads now have the active site on the actin to bind to, and so they'll bind to those binding sites, and they'll form cross bridges. Now, using the energy that's stored in the myosin, the heads will pull the actin filaments together. In each sarcomere, this is happening, and what happens is that whole cell will get shorter. But now we're left with myosin and actin bound together, and that's no good. The next thing that's going to happen is we're going to use a molecule of ATP, and that's going to break those cross bridges. So it's going to detach the myosin heads from the actin fiber filament, and it's going to move those myosin heads back to normal. And now that says it gets ready for the next power stroke. And what we're talking about, a power stroke, is when the myosin binds to the actin and moves backwards. So that moving backwards, that's going to be considered the power stroke. When the action potential is no longer there and the muscle relaxes, the calcium that was released at the beginning is going to be pumped back into the sarcoplasmic reticulum. That's going to cause the tropomyosin and the troponin to go back, cover over the binding sites on the actin, and that means that muscle contraction can't happen anymore. So that's a summary of what happens for muscle contraction. So for you guys, it's going to be really important to understand each step in that process and to know what happens. What I'm going to suggest that you guys do is have a look at these two videos on YouTube. They're really good, and they go over the exact same process that we just talked about, but there's animations there, so there's good examples of how all this fits together and how it all works. So what I suggest to do, watch each one of these videos, go over the previous two slides, and then watch these videos, and then go back over the slides and make sure you understand what happens at each step. Use the slides and the videos together so that you get a good understanding of this physiological process. Okay, so I'll end the video here, and that'll be the end of muscle contraction. And when we start the next video, we'll move on to a slightly different topic.